So this is, I believe, the final video for the electricity and magnetism unit for APC. And this is basically going to cover inductance in a circuit, which will be LR and LC circuits. It may seem like I'm leaving out Maxwell's equation. I may do one more on Maxwell's equations, but Maxwell's equations include the Biot-Savart law, Ampere's law, Faraday's law, and some laws about inductance. So I am not neglecting those equations. It's just that we've already covered them. Okay, so inductance is if you take this circuit, we have a circuit here with a battery and a resistor and a switch. If you immediately close the switch, current starts to flow through this circuit. Well, because a current carrying wire will create a magnetic field, that will produce a changing magnetic flux through the area of this circuit. We learned in the last video that a changing magnetic flux, not a magnetic flux at all, but a change of magnetic flux, will induce a current in a wire that will produce a magnetic field in the opposite direction to try to keep things at a steady state. And so, as you close this switch and the current starts to run out of the cathode of this battery and starts to increase in magnitude, it creates a magnetic flux going this direction, which would induce a EMF, a back EMF is what it's called, that would lead to, it doesn't actually change the current, but it slows down the rate of increase of the current. It's almost like inducing a reverse current, except the sum of the currents is still forward. But you induce a current in the opposite direction, again, much less than the current that's running out of the battery. And that's called a back EMF, and that's going to reduce the rate at which the current increases. If there were no inductance, if there were no back EMF, if there were no magnetic field, if there were no magnetic flux change over time, then when you close the switch, the rate of current increase would just be linear. But instead, since it is continually impeded by a current running in the opposite direction because of the changing magnetic flux in this area, the rate of current increase will actually be an exponential curve. And we're going to talk about that in just a second. But the induced current will be the induced back EMF will be, again, this negative indicates that it's in the opposite direction of the change of current. And this L term is something called inductance. And this is basically a statement of what we just saw with Faraday's law. Excuse me. So with Faraday's law, we saw that there's an induced electromotive force that will try to oppose any change in magnetic flux. Well, this is the same thing, but now we're putting it in terms of this new variable, which is called inductance. Well, inductance is N, the number of loops of wire, times the change of flux divided by current. And when you combine all those equations, you get that the back EMF, this EMF that's produced, is divided by the change of current is the value of the inductance. The unit of inductance is a Henry, and there are like components of circuits called inductors, which is where we're going with this. But the unit of inductance is called a Henry, which is 1 volt times second divided by amperes. Again, volt, which is the EMF, divided times seconds, because this went back to the top, divided by amps. So here we go. A coil with zero resistance has its ends labeled A and B. The potential is higher at A than at B, Which of the following could be consistent with this situation? Current is constant, the current is constant. It's definitely not that, because the only thing that's going to keep just a coil with zero resistance creating any sort of EMF or potential difference is going to be a changing magnetic flux, and the changing magnetic flux is only going to be caused by a changing current. The correct answers are that the current is increasing from A to B, which would create, like, that's why it's going that way, or it's decreasing from B to A. Not good. So we have a new circuit element, which is called an inductor. It's the squiggly do. Burkett, I am never going to forget that term, and I'm always going to use it. And the squiggly do, this is the most basic circuit you can have with a squiggly do, with an inductor, and that is a resistor and inductor. And here we have a battery over here. When you close switch 1, notice that would complete this big circuit here, where the current would come out of the battery, through resistor 1, through the inductor, and then back around to the battery. But the inductor, remember, is going to try to oppose any change of current. So as the current increases, this inductor is going to create a back EMF. Let's see, when the switch is thrown closed, the current increases, and an EMF that opposes the increasing current is induced in the EMF. So you create an oppositional EMF. This acts like kind of a battery, but only as the current is changing. Once you get to a steady state current, the inductor is basically straight wire, because the inductor only responds to a changing magnetic field, which is caused by a changing current. That change is the important part. Any current is fine. Once you get to steady state, this acts like the straight wire. But as the current starts to increase, as you close that switch, you start to get a back EMF developed, and that means that the current will eventually reach its maximum current value, which is the EMF divided by R, like voltage over R, V equals IR kind of thing, times 1 minus e to the negative t over tau. Our tau is slightly different from an RC circuit. In an RC circuit, tau was R times C. In an inductance circuit, an LR circuit, our tau is L over R. But that means that the current is going to increase, but it's not going to increase at a linear rate. And without an inductor present, the current would increase straight up. With an inductor present, since there's something impeding the rate of, like impeding that inductance, it's going to increase. Actually, no, I'm sorry. Let me take that back. Without an inductor present, the current would go straight to its maximum value. There would be no linear increase at all. I'm sorry. Let me repeat that one more time. Without an inductor present, the current would instantaneously change from 0 to its maximum value. But in reality, even the wire itself acts as a small inductor. But with an inductor, and there are components called inductors, with an inductor present, the current will increase, but there will be opposition to its increase. And so it will increase until it gets to a steady state. This looks very, very similar to what we saw for the charge developing on a capacitor. It's the same equation, even if you look back at the capacitor equation. So the current is going to increase. The rate of change of current starts off changing a lot, and then it goes to no rate of change. And once it gets to no rate of change, you're at maximum current, and the inductor basically has no effect on that circuit. The inductor only acts right when there's a changing current, which would be when you close that switch, or if you were to move this switch from this position. What is this? This is the current. This is the equation for the current. Oh yeah, so this is this. Let's go back to this picture. All right, so if you were to switch this switch from here to there, you've now basically taken the battery out of the equation, and so the current is going to decrease over time. If the current is decreasing, there will be an EMF developed which will try to increase the current in this direction, and that will change the current. It will still decrease over time, but it will not decrease instantaneously. Instead, it will slow down over time. And that is given by this equation. I is equal to I initial, which was your maximum current, times e to the negative t over tau. Again, this looks similar to graphs that we've seen with capacitance. And what I will probably do is, like, I'm probably going to write out all of these graphs for RC and LC circuits for you with the equations right beside them, so you can get a grasp of all of them, possibly with a couple notes. I also intend to go through and do some problems tomorrow morning and record me doing those, so I'll get some more calculus in there. And this is really interesting. This is showing the voltage across the resistor and the voltage across the, actually, there's a good quiz. So, consider this circuit where S1 is open and S2 is at position A. That's this initial right there, right here. Suddenly, S1 is closed. At the instant it's closed, across which circuit element is the voltage equal to the EMF of the battery? Well, at that instant, there's absolutely no current yet. And as the current increases, the inductor will oppose that current. But if there's no current, then there's no voltage drop across the resistor, because according to Ohm's law, the voltage drop across the resistor is equal to the current times the resistance. Which means that then that entire voltage drop, if you're going to continue with Kirchhoff's laws, which says that the voltage drop around a complete circuit has to equal 0, has to be from the inductor. After a very long time, across which circuit element is the voltage equal to the EMF of the battery? Well, after a very long time, there is no longer any change of current, and so as a result, the inductor just acts like a straight wire. And so all of the voltage drop has to occur across the resistor, right there. So the voltage across the resistor and voltage across the inductor have this inverse relationship, but they will always equal a constant value because they have to equal the voltage of the battery. Okay, energy is stored in an inductor. I mean, it's stored in a capacitor, it's stored in an inductor. And the amount of potential energy that is stored in an inductor is 1/2 Li squared, where I is the current. Okay. I'm not going to worry about that too much. I don't think you'll see that. All right, mutual inductance. This is how step up and step down transformers work. Basically, if you have a coil of wire over here, which has 1, 2, 3, 4, 5, 6 coils, and this one has, I don't know, 5. Let's say this was 10 and this was 5. Well, if you have a current of 5 in this, you will create a current, like the more coils, it'll increase the current, which will increase the voltage. So a step up transformer goes from fewer coils to more coils, and you just multiply by the number of coils, the ratio of the number of coils. Step down transformer, you divide by that number of coils, because it'll be more coils to fewer coils. But it's saying that if you have 2 coils together, it's related to this ratio of coils to each other. And the last part, LC circuits. So LC circuits don't contain a resistor at all. They're just a capacitor and an inductor. Notice a simple LC circuit, you have to like put some energy in from the battery, but then the LC circuit will actually, you'll flip the switch from A to B, And so the circuit will just run from the inductor to the capacitor to the inductor to the capacitor. Remember, a capacitor will develop a separation of charge across the two plates of the capacitor. And so it stores charge with that potential difference. An inductor is going to oppose a rate of change of current, or well, of magnetic flux, but that's related to current. And what ends up happening, and actually this is probably the best image of what's happening. You start here in an LC circuit, and all of the energy is stored in the capacitor because we've charged the capacitor. And you flip that switch, and that means once you flip that switch, the charge is going to run off of the capacitor. So it's going to come off of the cathode, the positive side of the capacitor, run around this way. Well, when it gets to the inductor will try to oppose that rate of change of inductance, and it will eventually develop a back EMF, like the charge will all run around to this side, but then the back EMF will send it back to this side, then it'll run around. The charge is going to run from this point to there, to there, to there. So, and this is showing it's very much like simple harmonic motion, where the energy went potential kinetic, potential kinetic, potential kinetic, potential kinetic, but now it goes capacitor, inductor, capacitor, inductor, capacitor, inductor. It goes from capacitor, all on the capacitor when the capacitor is charged, to all on the inductor when the current is at a maximum. And then as the current, deposits its charge on the opposite plate, then you have no inductance here and all of the energy stored in the capacitor again. And then it runs off of that plate and it goes back through the inductor. And so all of the energy is on the inductor. And then this is kind of like a halfway point. It's showing that the capacitor still has some charge, but there's some current flowing. We're not at maximum current. We're kind of somewhere in between. So the energy is split between those two values. But again, it's going to show that simple harmonic motion sort of thing, where the charge is going to go from capacitor to inductor, capacitor, inductor, and capacitor, inductor. And the current will vary 90 degrees out of phase. So when the charge is at a maximum on the capacitor, there is no current. And as the current starts to run and the current's at a maximum, there's no charge on the capacitor. And then when it's all on the capacitor, there's no current. And then when it's all running through the inductor, there's no charge on the capacitor, etc., etc. So this is, again, a simple harmonic motion kind of thing. And the energy switches between the inductor and the capacitor, and the inductor and the capacitor, and the inductor and the capacitor. And here's the equation for the energy of the inductor, and here's the equation for the energy of the capacitor. Again, it's always going to be positive, but you can see that they're 90 degrees out of phase. When this is at a maximum, that's at 0. When that's at 0, that's at a maximum, etc., etc., etc. Which is just so cool. And that is the last topic. I'm not going to go over RLC circuits with resistors and inductors and capacitors. I'd love to go over it with y'all if y'all want to see it after the AP exam, but I'm not going to include it in this video. And kind of here's the summary. But y'all also have access to your book. I will write out these graphs and their equations and post a picture of that on campus and send you an email. And I'll get all of the mechanics videos made either tonight or early tomorrow morning. Hope this helps.